Good morning, good afternoon. I would like to start this lecture by presenting some motivations coming from algebraic statistics. I hope you all remember the one-dimensional Gaussian distribution, that's a probability distribution, which has a generalization to arbitrary dimensions. So this is on R. In general, there is a distribution on Rn. And the density function, which you can still imagine as like a bell-shaped function, but in higher dimensions, now depends on two parameters. So in the one-dimensional case, there was the mean mu, and there was another number which told you how much spread is the distribution. So currently, we will still have a mean that is a vector in Rn, and the second parameter will be a symmetric matrix. This will be an n by n symmetric matrix. So by S to the second symmetric power, I denote the space of symmetric matrices. Now, this is called as the covariance matrix. In the one-dimensional case, the second parameter needed to be positive. Yes, the variance of the distribution had to be a positive number. And in statistics, in higher dimensions, this is reflected by the fact that sigma is positive semi-definite. In fact, positive definite, but okay, positive. Okay, and then we obtain the distribution on Rn. Maybe I will not give an exact formula. It's in the notes. It's still an exponential given by two vectors and sigma inverse in the exponent, and then there is the normalizing constant. It's not so important how this function looks like. Now, in statistics, what do? We have some process that first we have to assume what are the parameters that model this process. So say a statistician guesses that the process follows the Gaussian distribution on Rn, and then he or she would like to determine the parameters of that process, that is mu and sigma. Well, they would like to determine it based on what? They draw samples. So a sample means basically an observation, and it's like currently a point in Rn. And if we gather sufficiently many of such samples, yeah, we could start to guess how much our distribution is spread and in which direction and what's the mean. Okay, so what does it mean, guessing? Well, we have to make it more formal, and what we actually do is, so this will be our SIs, we compute the product of F mu sigma evaluated at the SIs. Now, if our distribution somehow has, for example, mean far away from our samples, then these values of this function will be small and this product will be small. This is called the likelihood function. And finding the parameters mu and sigma that best explain the observed sample is basically maximizing likelihood function. So our aim find mu and sigma that maximize the likelihood function. Okay, and this is more or less, I would say, a topic that that has been solved. Let me change the color. Well, first of all, the mean, as you can guess, will be just the mean of the points that that you are getting. There is also a formula for the sigma that best explains this observation, coming as an average, as a mean of sigma i's that are obtained from every single observation. You change an observation into a rank 1 matrix, and the mean of those gives you the best sigma. Okay, so if statisticians already solve this problem, what will we be actually after? So sometimes the model does not allow you to have arbitrary sigmas. So the statistician gives you more information and tells you that you should not expect sigma to be any positive definite matrix. And let me introduce one class of such models called linear concentration models. So first we introduce K, which is just sigma inverse the concentration matrix. And the linear concentration model tells us that K belongs to some fixed L linear space. Well, where is this linear space? So notice that if sigma belongs to S2V, then K belongs to S2V dual. Think about it, why the inverse matrix naturally belongs to the dual, and this K belongs to L, which is a linear subspace of S2V dual. Okay, so we have a map from S2V dual to S2V. Yeah, here we have a subspace. Here it maps to something that I will call L inverse. It will be a subvariety in S2V obtained by inverting all matrices from L. Now, I am being slightly informal here because you cannot invert all matrices in general from L because some of them could be not invertible. That's why I was drawing this arrow as a dashed one. And I will be even more informal because I will usually work in the projective space. Yeah, so we will have a map here. So I will work up to scaling the matrices, and I will also call this by L and L inverse. Okay, so usually formally L inverse denotes the Zariski closure of the inverses of all invertible matrices from L, where L is some fixed linear subspace. Now, notice that S2V contains one more very natural thing related to L, not only L inverse, which is a subvariety, but also L perp, which is the linear space of all linear functions on S2V dual that vanish on L. Yeah, so this S2V somehow naturally, from the mathematical point of view, contains those two objects. And again, I will abuse the notation, and I will say that L perp also lives here in this projective space. Okay, so from the point of view of statistics, what is our aim? We obtained those observations, and we got mu, and we got some best explaining, let's call it sigma hat, mu hat and sigma hat. So this sigma hat will belong here. Okay, but no one promises us that this belongs to L inverse. like Y, you should imagine something that you have a coin that has a probability distribution, let's say 40% of heads and 60% of tails. If you throw it 1,000 times, you will not get 400 heads and 600 tails. You will get something close. So even if the statistician correctly tells you the model, you don't expect that your data actually gives you a point on the model. So a new aim is to maximize likelihood function on L inverse, okay? And so not on S to V, not to find sigma, but you want something here. Now there is a good news. So I want to write it as a theorem. So we have, so in S to V, we have our sigma head, we had our L perp, and we have our L inverse. And there is also a natural projection to S to V divided by L perp, because these are just vector spaces. Let me call this projection pi. So the theorem sigma prime that maximizes likelihood function on L inverse is the unique positive definite matrix such that pi of sigma prime is equal to pi of sigma head. Okay, so in other words, what we want, I mean, the sigma head descends to a point here in this quotient, and we want to look at the fiber of this projection, which is a linear space, and intersect that fiber with L inverse. So so pi inverse of a point intersected with L inverse, this may consist of several points, but only one of them will be positive definite, and this is the one that maximizes the likelihood, and this is the one we look for. Okay, so so again, it seems that the subject is closed, but how complicated is sigma prime? How complicated is sigma prime? Well, this is basically governed by the cardinality of this fiber. Why? Because this basically tells you how complicated is the polynomial that defines the sigma prime. So sigma prime happens to be one of the solutions of linear equations added to the equations of L inverse, but the number of solutions it's in total tells you the measure of complexity of sigma prime. So a definition, this cardinality is known as the maximum likelihood degree. Okay, and of course it depends on L. It over the complex numbers in the projective space, it basically does not depend as long as the point is generic on the chosen point. So I here pass from the real to the complex, but the justification is that I am more interested in this number because this is the measure of the basic measure of complexity of the model. Okay, now there are two things. There is the degree of L inverse and there is the cardinality of this. And you could think that they are equal because if you're intersecting a variety with a linear space and you get points, then you should get the degree many points. And this is to some extent true. The problem is that if you are in a non-generic case, this can fail because the center of projection, L perp, may intersect L inverse. So your linear spaces might intersect L inverse not only in those finitely many points, that is the cardinality of the fiber, but also in the center of projection, which causes some problems. Fortunately, these problems do not arise in the generic case. So from now on, L will be is generic. Okay, and it's okay. So first of all, in this case, we only have the maximum likelihood degree. So we will always denote it phi n d, where d is the dimension of L. Yeah, so this is the maximum likelihood degree. Now, because L is general, we do not have to specify L. So this is just one number that just depends on the dimension of L. And further, there is a theorem by Tessier that in this case, phi and d is, as we would expect it, just the degree of L inverse of this variety. So why this is not obvious? So what he actually had to prove is that L perp is disjoint from L inverse in the projective space. Okay, so it's really important to realize why this is a highly non-obvious theorem. There are other proofs by Sturmfels, Euler, and so on. We provide, they are maybe more elementary, so we give them the references in the notes. Okay, so again, in the complex projective space, we do not have to anymore remember this projection pi, because we just want the degree of L inverse. So phi n d is the number of pairs of matrices K sigma in P S2 V dual times P S2 V, such that, well, they are inverses to each other. So K sigma is the identity. And well, K belongs to L, M belongs to M, sigma belongs to M. Where L, M are general linear projective subspaces. Okay, well, what's the dimension? Well, so this one has dimension d minus 1, and this one has codimension d minus 1. Okay, so that we actually get a finite number of points. So we managed to somehow translate the maximum likelihood degree into a kind of a counting problem. Okay, so let's try to do some math. So in this space P S2V times P S2V dual, we have pairs of matrices K inverse, and we can close it up. So what happens when we close this variety? So we have K and sigma here. So there are two options if K sigma belongs to X. Well, one is, as we would expect, that K times sigma is identity or proportional to identity if we work in the projective space. But it turns out that in the closure, we also have that K times sigma is equal to 0. We also have such points. And in principle, what we want is we want to intersect X with hyperplanes here and with hyperplanes here until we get points and count the number of those points. So we could do the computations in the Chow ring of X, but this is hard. As X is singular. Okay, so that is why we would like to, or at least when n is large, X is singular. So we will replace this. So our aim, replace X. And we will replace it with a so-called variety of complete quadrics. Okay, so before I will define the variety of complete quadrics, I want to give you one example. So let us look at the space of quadrics in 3 variables, which I will denote as 2v. And well, first let me answer an enumerative problem. How many quadrics pass through 5 general points? Well, passing through a general point in let's say in V dual, this is a hyperplane condition here. Make sure you understand it. So what we have to do is we have to intersect H1 with H5, which gives us a point. So the answer is that there is a unique up to scaling quadric passing through 5 general points. Answer 1. Okay, so now let's try to ask a different question. How many quadrics are tangent to 5 general lines? And we could proceed as before, that is, being tangent to a line, this is a quadratic condition in this space. So we are intersecting Q1 with Q5, and what we should do is like have 32 points. Okay, 2 times 2 times 2 times 2, 5 times. Okay, but let me give you a different answer. Well, being tangent on a plane to a quadric, this is equivalent in the dual space that the dual quadric to a quadric, which is a set of all tangent lines to a given quadric, that's also a quadric in the dual space. If you don't know a dual quadric, please read about it, that it passes through the point corresponding to the given line. So in this dual thing, in this dual point of view, we are counting how many dual quadrics pass through 5 given points. How many dual quadrics pass through 5 points? Well, we already solved these problems. If the points are general, there is 1. So we expect 1 dual quadric. So what happens? Here we got 32, here we got 1. Well, these 2 numbers are not equal to each other. And the answer is that these quadrics are not transversal. They all vanish on rank 1 quadrics in this projective space, on a variety. So actually what happens is that this intersection consists of rank 1 quadrics. This is infinitely many. positive dimensional thing, plus 1 point. And this 1 point is the smooth quadric that will be dual to that one. Okay, so one has to be slightly careful with doing Schubert calculus, and one really has to make sure that that we are on the correct space where our, let's say, divisors intersect as they should. Okay, so to remedy all these problems, we now introduce the space of complete quadrics. For a matrix, let me denote by this the kth compound matrix. There are a few ways to define it. One way is in the basis. So the entries of this matrix are just k by k minors of the matrix A. Another one is that you can look at the matrix as a linear map. And then if you have a linear map, you can take a wedge of that linear map. And then it's a map between the wedge product of the domain to the wedge product of the codomain. It's still a linear map. And this would be our wedge K. A. So in particular, note that if we will always use the convention that V is n-dimensional, sorry, so n equals n is the dimension of V, then the n minus first compound matrix of A, this is basically the adjugate matrix formally, but you can really think that up to scaling and up to isomorphisms, that's like the inverse matrix. Okay, so we start with the definition. One of the definitions of the variety of complete quadrics. Well, if we have a symmetric matrix, we can associate to it, well, the matrix itself, then the first the second compound matrix, and so on, up to the n minus first one. Yeah. So notice that this belongs to S2 wedge KV. Okay. So this just sends A to A, comma, wedge 2A up to wedge n minus 1 A. Okay, this is a rational map because it could happen that for example this is 0 and we want to be in the projective space. So the variety of complete quadrics is the closure of the image of this map. Okay, so a typical point you can think as such a tuple where all these matrices are invertible, but because we take the closure, there are more points, and in the notes you can find a very explicit example where we show that in the limit you get additional matrices. Okay, so now notice that this one, yeah, this one, or in general wedge Ka, we can regard it as a quadric on the space wedge Kv. And in particular in wedge Kv, the Grassmannian lives. So we can ask what locus of K-planes does this quadric cut out on this Grassmannian? And the answer is very geometric and very nice. Wedge Ka as a quadric on the Grassmannian, as quadric on GKV, cuts out K-planes, finally K-planes projectively K-1 planes that are tangent to the quadric? Given by A. Okay, and there is complete proof in the notes. It's not very difficult. For the sake of time, I will skip it. Okay, so how to imagine points of complete quadrics? Well, one, as I said, if you, for example, want to imagine sets of a Grassmannian, you can imagine a smooth quadric. Then you can imagine the set of its point, which is just the quadric itself, a set of tangent lines to that quadric, which is a subspace in the Grassmannian of projective lines. And there, the set of tangent lines to the original quadrics is also cut out by a quadric, which you have to remember. Then you take tangent planes, tangent three planes, and so on. Each of those will be given by a quadric condition in a Grassmannian, and you have to remember all of those quadrics. Now, all those quadrics, if your starting quadric is smooth, they are uniquely determined by your starting quadric. So you can always imagine them as sequences like A1 up to AN minus 1. But if your A1 is smooth, then the other ones are just the compound matrix of A1. So the question is, what happens when A1 is singular? Yeah. So let's say that the determinant of A1 is 0. Well, there is a recursive description of points on the variety of complete quadrics, where basically, if you have the image of A1 to be some subspace, let me call it U, then what you have to remember is A1, so A1, and it turns out that A1 does not uniquely determine the point of complete quadrics. You additionally need to remember the point on the smaller variety of complete quadrics, V divided by U. Okay, so if your matrix is degenerate, you need to remember more information than just a matrix. The point in the variety of complete quadrics gives you additional information. Okay, now let me give you one more very explicit geometric, but maybe not so explicit when it comes to points, explanation of the variety of complete quadrics. So we have S to V, which let me call X0, and this contains the locus of matrices that are rank 1. And if you know the construction of blow up, we will blow it up. Now, in this X1, we have a strict transform. So in other words, we pick a rank 2 matrix and we look at the rank 2 matrix. And if we do that for all rank 2 matrices and close up, that's called a strict transform of rank 2 matrices. And we may blow that up. And we do this. The last thing we blow up are matrices of rank n minus 2. We don't blow up matrices of rank n minus 1 because they form divisors. And it turns out that this is exactly the variety of complete quadrics. That's a very, very direct geometric interpretation of the variety of complete quadrics. In particular, you see that it comes with a map to PS to V, which from the previous picture you can also see as a projection. Okay, so this variety of complete quadrics, in particular from this description, but not from the previous one, you can see that it is smooth because it's just obtained as a sequence of blow-ups. Okay, so in the last 10 minutes, I would like to present some examples of this variety of complete quadrics. So the first example will be really trivial when n is equal to 2. And then the map that takes the inverse matrix of a 2 by 2 matrix. Okay, so it looks like it should not be well defined because you cannot invert every 2 by 2 matrix, but on a projective space you can, because if you multiply by the determinant, you will actually get a linear isomorphism. Okay, and in this case we have that PS2V is isomorphic to the variety of complete quadrics. It's also isomorphic to our variety X, that was the graph of this map. So in general, both of those fail because the graph can be singular and the variety of complete quadrics is obtained as a blow-up of this, but in this small case, all are equal. But even here, we can see something interesting, that this variety of complete quadrics comes with two types of divisors. One comes if we just take a hyperplane here. This gives us a hyperplane here. But there is a second different divisor, namely rank 1 matrices. Yeah, rank 1 matrices, they give a quadric here. Yeah, because that's the determinant. They are cut out by the determinant, and I wanted to stress this, that there are two types, naturally two types of divisors of on the variety of complete quadrics. We will see more on about that later. Now I wanted to describe the case, what happens when n equals 3. So now PS2V, this is actually a rational map. So maybe surprisingly, again, it's defined on the map, on the locus of rank 2 matrices, but it is not defined on the locus of rank 1 matrices, because if you take 2 by 2 minors of a rank 1 matrix, you just get 0. Yes, so, and this is not a pointer on the projective space. So our variety of complete quadrics, it's actually a blow up at the rank 1 locus. So it comes with maps here, and this is a blow up of rank 1 locus. Okay, so it lives in the product, so it is contained in PS2V times PS2V dual. So a pair of matrices that belongs to this CQV, well, there are a few options. Either A has rank 3, and in this case, B also has rank 3, and it's just the adjugate matrix to A. So in this case, you can reconstruct A from B, you can compute B from A. And this is somehow a general situation. So a general situation looks like this, that you have two rank 3 matrices that are inverse to each other. Okay, now another situation could be if A has rank 2. So if A has rank 2, then the image point is still well defined. I mean, this on rank 2, this is still an isomorphism. So there is a unique matrix B which has rank 1. Okay. Yes, and in particular, notice that one thing that may be strange here is that you will not be able to reconstruct A from B, because if you will get another rank 2 matrix with the same image as A, it will give you the same matrix B. So A uniquely determines B, and now we can have rank 1 matrix A, and then there are two cases. B could be rank 2, or B could be rank 1. Now, B rank 2, this is very similar it's just dual to the case above of A rank 2 and B rank 1. So here the situation is that B uniquely, if you know B, then you uniquely determine A, but A does not uniquely determine B. B could be any matrix that vanishes on the image of A. And then there is the case where B is a rank 1 matrix that vanishes on the image of A. So this is yet another possibility, and all those points actually appear in the variety of complete quadrics. In the notes, we have added quite a few pictures that we hope explain well what is going on and how this degeneration process proceeds. I will maybe try to reconstruct one of the series of those pictures. So if we take a quadric, a plane quadric, the dual quadric, well, you can imagine it as a set of tangent lines. Yeah, so this is a quadric in the dual space. Now, let's say we will be degenerating this quadric, so we will be making it looking like this, and like finally as a double line. So what happens to the tangent lines when we flatten our quadric? Yeah, so it's not true that you will obtain any line in the limit. So in other words, we want to say what's the limiting object. But if you think about it, this quadric, the way we degenerate it to two lines, there are these two special points. Yeah, and basically every single line will be getting closer to those points, and in the limit we will get so I should have used different colors for the tangents. Yeah, so every tangent line is a point on the dual quadric. Yeah, here we take tangent lines. Yeah, and here we take. So I'm claiming that the limits of those tangent lines will be just lines going through 2 points. So to answer the original question, lines going through a given point, well, they form a line in the dual space, and line going through another point, they form another line. So this quadric will degenerate to 2 lines. Yes, and somehow in the complete quadrics you have to remember this information, how you degenerate it. There is slightly more duality here, namely this point on intersection, it's a line. Well, which line? The line that goes through both of those points. So it's the unique double line. I mean, it's a line that is the same as the double line to which our quadric degenerated. Now, the way we have constructed complete quadrics, so the blow-up definition completely does not make it clear, but the compound matrix definition already makes it slightly clearer that there is an isomorphism of the variety of complete quadrics on V and on V dual, where we just have to exchange, that is, we have to on this product of spaces where we have S2n minus 1 V. Well, so what we need to do is we need to somehow identify wedge k V with S2 wedge n minus k V dual. And this is like we were doing in a Grassmannian. So a k plane in V can be identified with an n minus k plane in V dual. Yeah, so that's why we, oh, sorry, I forgot the projectivization. So now we switch. I will first put this, but I will use this duality, and this will be P S2 V dual. Yeah, so the n minus first wedge power will go to V dual. Then there is time P S2, and then the first one here will be just wedge 2 V dual, and so on. And this one will be just the projectivization of S2 wedge and -1 V dual. Okay, so so in fact this variety of complete quadrics it makes the inversion morphism. So notice that this is a birational map, but it doesn't really matter if you go from V to V dual or from V dual to V. Inversion is inversion, and this variety of complete quadrics is very symmetric with respect to that construction. Okay, so what will happen in future is that our counting problem, which was a problem of counting pairs here, we will lift it up to the variety of complete quadrics, where, as we will see, the solution is much easier. And the variety of complete quadrics is smooth, and the systems that we will get will have no base locus. So actually everything will boil down to understanding well the Chow-ring of the variety of complete quadrics. Thank you very much.